Hello, in this lecture we're going to talk more about one-dimensional motion. The study of motion, that is analyzing a motion mathematically, is called kinematics, and we're going to restrict ourselves to kinematics of constant acceleration. It is a pretty common phenomenon in nature, so it is not far-fetched from the real idea that we study constant acceleration. Gravitational motion is a very good example of constant acceleration. Constant acceleration means that throughout the journey, throughout an object's motion that you're observing, the acceleration remains constant. And in doing so, the acceleration is equal to the average acceleration, right? Because it is the same value throughout. And we know that average acceleration is equal to Vf minus Vi over Tf minus Ti. So studying constant acceleration is easier because we can use the definition of average acceleration like this and build equations from it. Another equation that we can use for constant acceleration is that if the acceleration is constant, that means velocity is increasing uniformly. What does uniformly increasing velocity mean? Well, the velocity change is in equal periods of time is the same. So that makes life easier for us, and we can say that the uniformly increasing velocity gives us, or uniformly changing velocity enables us to use the definition V average equals to Vi plus Vf over 2. So when acceleration is constant, V average can be considered to be basic arithmetic mean. Okay, just the average. From these two equations stems out the kinematic equations of motion. So we end up with 5 equations from these two building blocks. I don't want to go over the derivations because those have been done a million times before, and our goal really in physics is to use equations and solve real life problems. Okay, so we have 5 equations and 5 variables. All of these are motion variables. So the idea of each of these equations is each of these equations have 4 variables. So if you want to find one variable, then you need probably 3 more variables to solve for that 4th variable. Or if you flip the coin, we can say that if you're given 3 variables, then choose the equation that enables you to find the 4th variable. Let's go over an equation like this. So here, first equation is Vf equals Vi plus At, where Vf is the final velocity, Vi is the initial velocity, plus acceleration is the constant acceleration of the object moving, and delta t is the change in time for that duration of motion. Okay, so if we want to say find delta t, and we know Vf, Vi and A, this would be a good equation to do. Okay, and second equation is delta x equals 1/2 Vi plus Vf times delta t. Delta x is the change in displacement or total displacement, Vi again initial velocity, Vf in final velocity, and delta t is still change in time for that motion. So here, if we want to find, say, the displacement, and you know both the initial and final velocities along with the time, this would be a good equation to go. Similar, you can think of all the 3, 4, 5 equations as well. And if you look at the variables that are in these equations, 4 of the 5 variables are vectors in red. So del x is a vector, Vi is a vector, Vf is a vector, A is a vector. So for all these vectors, the sign in front of them is very important. So make sure when solving these problems, define a consistent coordinate system and choose your signs of your vectors relative to that. And we will see in examples what we mean by that more clearly. And the most important thing to realize about these 5 equations is that these 5 equations are only valid for constant acceleration. So if acceleration is changing, then you cannot use these 5 equations in problems to solve for any of the variables. Okay, let's look at an example here. So let's read the question together. A cyclist traveling at a speed of 4.2 meters per second due north accelerates at a rate 1.1 meters per second squared. In a period of 7.4 seconds, what is the distance covered? So let's see what we are given. We are given that the cyclist is moving at a speed 4.2 meters per second and gives me a direction which is due north. So in total, we have the velocity 4.2 meters per second due north. What kind of velocity is that? That's the initial velocity, okay, because that's when your motion or your investigation of the motion begins. Accelerates at a rate 1.1 meters per second squared. So, and this is assumed to be constant. So this is my acceleration, which is constant. In a period of 7.4 seconds, what is the distance covered? So period is another word for time. So in 7.4 seconds time, what is the distance that the cyclist covers? So our target variable is the distance covered, okay? Now, because it's constant acceleration, we will be able to use either of these 5 equations, whichever one suits best for our purposes. If the acceleration wasn't constant, these equations would not be valid anymore. Okay, let's see if we can solve this problem. First of all, as always, draw a simple figure. Draw a simple figure to help you guide yourself through the problem. Let's see. So let's first define a positive direction. So I have defined left to right as positive. So anything going from right to left would be automatically negative. So we have the cyclist at initial time 0. That's when I just see the cyclist moving. So initial time 0 seconds, and riding the bike at a speed 4.2 meters per second, and then I also see him accelerate at a constant rate, which is 1.1 meters per second squared. Okay, now if he does that then and continues this sort of motion for 7.4 seconds, so TF would be 7.4. What is the total distance covered in this time? Okay, then note down all of the variables in a nice manner. Vi is equal to 4.2 meters per second, which is moving in the positive direction, so it's positive. Remember, apart from time, everything is a vector, so you have to be very careful with what sign you are using. Vi is this. Do we know Vf? Not really. We are not given. We are not told anything about the final position. Do we know acceleration? Yes, we do. It's constant at 1.1 meters per second squared. Then what else do we know? We know that delta t is 7.4 seconds because Tf minus Ti is 7.4. So we know delta t. Do we know anything else? 1, 2, 3, 4. We know 3 out of 4, and we don't know anything else. And what do we want to find? We want to find delta x. Okay? So, which equation would you use to solve for delta x with Vi given to you, A given to you, and delta t given to you? So we need an equation with delta x, delta t, A, and Vi. Okay, so let's see which equation suits that. This doesn't have delta x, so we can't use number 1. This has delta x, so let's see. Vi, yes. Vf, we don't know Vf. So there are two unknowns in this equation. We don't want to go there. We won't solve this. Number 3, delta x, yes. Vi, yes. Delta t, yes. F is a constant. A, yes. Again delta t, yes. So this would suit our purposes. So we would use delta x equals Vi times delta t plus 1/2 a delta t squared. We want to find what delta x is. So Vi, what is Vi? It's 4.2 times delta t is 7.4 plus 1/2 a is 1.1 and delta t squared, which is 7.4 squared. So what is delta x? Delta x is 61.2 meters. Okay, but we are not quite done yet, because if you remember, when I wrote down these equations, I said that delta x is the displacement. So what is the difference between a displacement and a distance? Displacement is a vector. Distance is the magnitude of that vector. Distance is the magnitude of displacement. So even though delta x gives you a positive number, it could have given you a negative number, denoting that the cyclist was going the other way. So we need the distance. So from there, the distance is just the magnitude of whatever delta x you found, which is absolute value, which is always positive. So distance would be 61.2 meters always, but displacement could have been negative 61.2 meters. Okay, so you were asked to find distance. So this is what we were looking for. Okay, let's look at a more detailed example. So we have two of the best soccer players in the world, Cristiano Ronaldo, CR7, and Lionel Messi. They are playing against each other, say in a World Cup final, and the question is about that. So let's imagine that Cristiano notices Messi dribbling with the ball towards the Portuguese goal at a constant velocity of 20 miles an hour. So constant velocity of 20 miles an hour, this is for Messi. So anything in red is for Messi. So Messi is running towards the Portuguese goal at a constant velocity of 20 miles an hour. The Portuguese goal is 83 meters ahead of Messi. 83 meters ahead of where he started. Right? So this is where we start the study of motion. Now, Cristiano notices this run from Messi and he doesn't want Messi to score. So what he does, he tries to sprint and catch up to him. So CR7 starts from rest. So CR7 in purple starts from rest. When he notices the run, sprints at a constant acceleration in an effort to stop Messi from scoring. When he starts, CR7 is 95 meters away from Portuguese goal. What do we want? Our target variable is what is the minimum acceleration that CR7 needs to stop Messi. Okay, I would erase this board to make some space. So I would encourage you to write the problem down by pausing the video. So let's work on a solution. Again, first we want to draw a simple diagram to make our lives easier. Okay, so let's see what that simple diagram may look like. So anything in red was messy. Let's use red for messy. Messy is here, M, and he's running or dribbling at 20 miles an hour, pretty fast, but he is one of the best ever. And then Ronaldo, let's call it R, sees the run and wants to catch up to him. So he was initially at rest. So rest means stopped, which is a speed of 0. Okay. Messi was 83 meters away from the Portuguese goal. This is the goal. Okay. And when Ronaldo started, he was 95 meters away from the same goal. All right. And Ronaldo, to catch up to Messi, accelerates at a constant rate. Let's call it A. Okay. But Messi was running at a constant velocity. Constant velocity means velocity wasn't changing. If velocity doesn't change, acceleration is 0, because acceleration is defined as change in velocity over change in time. Okay. Now our second step is make two columns. One for CR7 or R, and one for Messi. Okay, and note down all the variables that we know. What do we know? CR7, VI starts from rest, so 0 meters per second. Acceleration is unknown. This is our target variable. Oh, and let's say we take this direction to be positive. I always keep forgetting this, but that is very important. So remember, always define a clear positive direction before you start the problem. What else? Ronaldo, displacement of Ronaldo that he needs to get to the goal is 95 meters. Okay, and do we know anything else? No, we don't. We don't know the time as well, right? Okay, so let's move on to Messi. We know that VI is 20 meters per second. Okay, and A is, we know, 0 meters per second squared, because actually this is not meters per second, this is miles an hour. Miles per hour. Okay, and what else do we know? We know that Messi's displacement away from the goal was 83 meters, right? He needed to cover 83 meters to get to goal. All right, and we don't know how long he takes to get there, and but we know that since velocity is constant, it is equal to VI, which is 20 miles an hour. Now it's a good idea, because units are all over the place. We have to make sure that miles and hours are converted to meters per second. So I have shown you how to do that, so I think you'll be able to do that pretty easily by now. So I'm not going to work it out, but you should for practice. Okay, so now that we have noted down everything that we know about both players, we want to highlight that this is my target variable. So if I look at any of the equations, but do we have enough information to solve for any variable? Well, not from Ronaldo's point of view, because we only know 2 variables out of 5. So that's not enough to solve a kinematic equation. From Messi's point of view, we have Vi, we have delta x, we have Vf, and we have A. So maybe we can do something about something from Messi's point of view. But remember, our target is not Messi's variable. Our ultimate target is Ronaldo's variable. So let's see what we can do with Messi's variables. As a common rule of thumb, when we have 2 objects or 2 separate objects moving in the same motion that you're studying, we have to remember that there is everything else, all of the variables are almost independent apart from one. Time relates the 2 objects. So in this case, Messi's time and CR7's time has to be the same. Why? Because we are investigating if CR7 will catch up to Messi. If we want to know how long it took Messi to cover whatever distance that was, 83 meters, and if he did that, then it's probably likely that he scored already, and we'll use that time in Ronaldo's variables and see in that time, did he cover at least this distance to stop him, or did he not? Right? That's how time relates the 2 people here. Another thing is, whenever you have constant velocity, it's often not a good idea to use Vi and Vf in the same equations because they're the same numbers in this case. So we'll try a different route. We'll use Vi, we'll use acceleration, and we'll use delta x to find delta t. Okay. Now remember, delta t is nothing but Tf minus Ti, and we can always set this initial time most of the time to 0, and let's call this Tf is t. So delta t is actually just t. All right. So let's find an equation that will help us solve for t, but also has delta x, a, and v in it. First doesn't work because we don't want to use Vf and Vi in the same equation because acceleration is 0, so we won't get anywhere. Delta x is a necessity, so but again we don't want to use Vi's and Vf's here together. Equation 3, well, we have delta x, okay, Vi delta t plus 1/2 a delta t squared. So that's a pretty good equation, right? Because we have most all we need. So we use the third equation, which is delta x is equal to Vi delta t plus 1/2 a delta t squared. Now a for Messi is 0, right? This is all for Messi. So delta x becomes, Vi was 8.94 meters per second times delta t. Now delta x, let's say he covered the full length to the goal, 83 meters. Therefore, delta t, I was calling t, so t equals 9.28 seconds. Okay, so now we are free to use this as a time for Ronaldo as well. So now that we have found the time, we can look back in Ronaldo's variables given. We know Vi, we want to find A, and we assume that in this given time Ronaldo actually catches up to Messi and covers more distance, which may not seem logical, but it is what it is. And then we have the time. and we want to find a. So we can again use the same equation because we have the same variables that were involved in this part of the problem. So let's erase this side and make some room. So we have delta x is equal to vi delta t plus 1/2 a delta t squared. So vi for Ronaldo is 0, so this term goes to 0. Delta x is 95, 1/2 a delta t squared, which is 9.28 seconds squared, and we want to solve for a. How do we do that? Let's take 2 on the other side by cross multiplying. So 95 times 2 equals 9.28 squared over a. Divide both sides by 9.28 squared. Alright, so a becomes 95 times 2 over 9.28 squared, which is 2.21 meters per second squared. So what is this? This is the acceleration that Ronaldo needs to reach